Okay, we're going to try another example relating to related rates. Okay, this one says a cube is expanding so that its volume increases at a constant rate of 10 centimeters cubed per second. So we have a cube and it's expanding so that its volume is constantly increasing at this rate. Find the rate of change in its total surface area at the instant when its sides are 20 centimeters long. Okay, let's think. What are we asked to find? We're asked to find the rate of change in the total surface area. So that's a rate of change. So that's a derivative of the total surface area. So there's a key right there. I need to find the total surface area. Okay, and then I'm going to derive that to find dA or dA dt or whatever that is. Okay. We're given some initial conditions here. We know that the time that we're interested in is when the sides are 20 centimeters long. And we're also given another variable when we have a volume. We have a volume of this cube, and the rate of the volume is changing at 10 centimeters cubed per second, so that looks like that would be a dV dt or something like that. Okay, so let's start first by drawing a picture and just seeing what it is that's happening. Okay, this may seem silly, but it usually helps a lot, so I would highly recommend it. Okay, so let's start with some variables here. Okay, this is obviously going to have a volume. It's growing. It's getting bigger and bigger and bigger as time passes at this constant rate. It's growing at this rate. We need to see what our variables are. So this is changing, and this is changing, right? So we have the same variable being used here. So we have V equals, the volume of a cube is just x cubed. All right, so there's one. Let's see, that looks like a relationship. Okay. Is there another relationship here? That still doesn't help me answer my question fully because I'm asked to find total surface area, right? So let's say A is my surface area, and what would the surface area of this be? There's 6 sides on a cube, and each of those sides is x squared, so we would say 6x squared. All right. Now we're also given the rate of change of the volume. So if I were to differentiate this, I would, with respect to time, I would find the surface area, or sorry, the rate of change of the derivative, the volume. Sorry. So let's try that. dV dt. I'm going to implicitly differentiate both of these. dV dt is equal to 3x squared times dx dt. And remember, I'm doing implicit differentiation, so I'm deriving all of the variables with respect to time. What would this be then? I'm asked to find the rate of change of the total surface area. So I have the surface area formula, but I need to find the rate of change of this. How fast is this moving? So let's see what we get here. If I differentiate both sides, I get 6 times 2x to the 1 dx dt, right? Implicit differentiation. This is just the chain rule. I'm doing 2 times x. This is the derivative with respect to x times the derivative of x with respect to t. Okay? Now, so this becomes really just 12x dx dt, right? So there you go. We have now we have two formulas, okay? Are they related? Could we relate them? Yes, okay? Let's see, what information do we have? We know that the dV dt, okay, when x is 20 centimeters, we know that dV dt is going to be moving at a positive 10 centimeters cubed per second at this rate, okay? And now I need to find dA dt, right? This is what we're looking for. This is my goal. And let's see. I have here, in these two relationships, it looks like I could combine these, right? I have a dx dt here, and since I don't know the dx dt, maybe I could combine these or somehow solve this and plug it into here to find dA dt, right? Okay. Do I even need the area? No, I don't need the area at all. Okay, so these three are what I need. Maybe I can use this information at this instant to find dx dt. So let's do that. Let's find dx dt then, since I know dv dt and I know x. And so then I could find the rate of change of x with respect to time at that particular instant. So I'm going to do that down here. Dv dt is equal to 3x squared dx dt. So that would make this, if I just use substitution, I would have 3 times 20 squared dx dt. All right? And so what would dx dt be then? If I were to move everything over to this side, this would be 10 over 3 times 20 times 20, right? So that would cancel. That would be 1 over 3 times 40, which would be 1 over 120, and that would be equal to the dx dt. Okay, sorry, I'm not being very clear here on my steps, but this is basically what I would get here, right? Now that's not my final answer. This is now going to help me find dA dt. Okay, so since I have this, I'm going to plug it back into my dA dt formula. I have 12 times x, which was 20, and dx dt now we know at this instant of time, this is all in one instant of time, right, is 1 over 120. Okay? And now if I evaluate this, I will be able to find my rate of change of for the surface area. Okay? So this becomes, I think that simplifies to 2. Okay? That simplifies to 2. We end up with 2 centimeters squared, because this area per unit of time. So 2 centimeters squared per second. And that is my final answer. Okay? So in this case, I guess it was a little bit different because we didn't necessarily combine these, okay? But you probably could have combined it up here even, and then found one differential equation, one big one, and derived both sides, and that would have been fine as well, okay? We chose to do it separately, and that's okay as well.